Oi, enhancing transformer training efficiency with dynamic dropout. Very weird paper for you here today, all right? First up, this is proof and a demonstration for all of the amateurs out there that you can, in fact, do an AI experiment and post it to archive, even when it's very, very small, all right? Just for sake of getting your work out there, have an interesting idea, etc., etc. This idea itself actually wasn't crazy interesting, but it is like worth looking into, obviously. But despite that, they are in fact it's roughly amateurs it seems. And they did post. That's amazing, and we love to see that. The issue being they just, in my opinion, did not do a very good job. So today we're taking this paper as a learning experience and a demonstration of how you, the amateurs watching, as well as the experts, I guess, can be curious about this, but mainly the amateurs I'm talking to right now, the amateurs, you can post to archive your own ideas and your own experiments, even if they're very, very small. But I want you to do preferably better than this one did because there's just lots of issues with this paper. But you know what? It is always room for improvement, and that's what I hope that they will do with a version 2. All right, let's get to it. So they are messing with dropout. If you didn't know, dropout is when you take a random fraction of the input units of the actual neurons and values, and you just randomly set a fraction of them to zero during training through each forward pass, which basically helps in reducing interdependent learning among neurons, meaning that if you don't use dropout, it's possible for the network to become over reliant on specific neurons, where like the gradient just puts it in a way that, oh, this specific neuron gets way too important. But with dropout, because you're constantly and randomly setting neurons to zero, it basically forces the network to not over rely too much on one neuron because in a given forward pass, it would then not have access to said neuron some percent of the time, right? So what they want to do here today is adaptive dropout techniques, meaning usually in training, we set our dropout fraction, our rates, our percent chance equal to usually zero point 0.1, I believe. And that's just every single neuron has a chance of zero point 0.1 to be dropped out and set to zero. But adaptive means that over the course of training, of the entire training run, we are going to change our actual rate of dropout, right? Now, this is where we start hitting the first of my many red lines through this paper. This is, of course, a first draft paper, so I'm not trying to be too mean. I will be mean in tone, but please take it as constructive criticism and as a sign on any amateur work you, the viewer, might choose to do in the future to just get people to edit your paper, get someone who knows the doing to actually look at it, like go on Discord servers and things and ask for reviews, stuff like that. And make sure you publish a version 2 and a version 3 once your version 1 is up on archive because there will be errors. But first up here, they were supposed to do a related work section about adaptive dropout techniques about previous versions, and they didn't hear, they just started talking about layer normalization, which is an adaptive normalization, regularization technique, I guess you could call it that, but it's not adaptive dropout. There was no reason to put layer normalization here. I do not know if there is any prior work on adaptive dropout techniques. It's one of those things with this field, there's just so many hyperparameters to mess with. I wouldn't be surprised if there's not, but I would probably assume in this case that there are, and it seems like they just did not look for any, is my guess. Actually, you know what? Let me do a really quick search. Adaptive dropout. First result, definitely. As I keep scrolling through here, I actually don't see much in the way of adaptive dropout. Maybe that's just a term issue. We're searching the wrong term. But like I said, I wouldn't be too surprised if there really isn't much work in this domain. And I would expect most work to have been done would have been a long time ago. I believe dropout's pretty damn old. And so we might have just been like all of the actual tests of this idea might have been back when we were still doing feed forward networks or something back in the 90s. I have no clue. But at least from here, I only see one paper using the actual term adaptive dropout. But anyways, first, and I believe major error already start off. This is like in a normal scenario, if I saw this, I would just stop reading the paper because I'd be like, this is, what are you doing right now? I did keep reading it because I want to keep it as a learning experience for the channel, not so much because I think that that's like a amazing paper per se, but it is worth all of the amateurs or the portion of my viewers who are amateurs watching my channel to see. So by adaptive dropout rate, what we mean is the dropout rate is a probability, right? And here, instead of one constant probability throughout the entire time, we have an initial dropout rate, P naught, and then a final dropout rate, PF. And then we have to, at every given time step, or every given training step T, we have to choose the in between those two rates, what's it going to be. And we're going to use a different function, some kind of decay factor to determine how quickly and in what functional form we actually go from P naught down to PF. The first one obviously being just a linear schedule, nothing complicated there, just a straight line. Then we have an exponential decay schedule, which is a more aggressive reduction in the early stages of training and then barely like asymptotically almost reducing in the later stages. And then they list off a validation loss based adjustment where basically they say they don't describe this. I need pseudocode here. They have no math, no pseudocode. I don't know how this actually works. All they describe it as, this is another big error here, is they describe it as when the validation loss improves, the dropout rate is decreased, otherwise it is increased. This doesn't make any sense. Like, what if it just keeps increasing? What if like we had a big gradient spike? What by how much do we actually decrease the dropout rate or increase dropout rate? It makes no sense, right? Um, and the last one that they didn't even include in this dropout rate schedules, they just forgot to list it off and then put it back in the results later, is they also have a cosine decay rate. This is absurd. They must have some kind of like internal deadline in their company to publish something or something silly, because this is just blatant lack of any type of fact checking, consistency checking, anything. Again, if you're doing an amateur paper yourself, please make sure to read it a second time. But the idea here, anyways, in terms of dropout decay, I do think is interesting. The way they actually implement this dropout scheduler is they create an update dropout function that is called at each iteration during training, so probably right before the forward pass. Doesn't really matter where exactly, but and then it adjusts the dropout rate. The way to adjust it is just by iterating over all dropout modules in the model. So for any nn.dropout, we'll just iterate through all of them. I'm not sure I'm super fond of this technique, doing that whole iteration. It might have been better to just use an actual dropout function in the model itself or something, and a global variable for the actual rates. I'm not quite sure. You'd have to test different methods that would attempt to decrease the actual wall time of this forward pass in each training iteration. Not sure would have been better, but this is fine totally for a first attempt implementation wise. Now, here's where I said that they're like very much amateurs doing a very small data set, and we love that, even if it's not actually robust and we can't really learn much from it. It is a first step in them expanding later, and I'm totally cool with them posting now and then doing a bigger data set later. The data set they used was, they call it Shakespeare. It's tiny Shakespeare, whatever. And I don't even know if they actually reference the original Carpathy source. I'm not quite sure, but they just call it Shakespeare character level data set. It's just tiny Shakespeare that like Carpathy loves to use. And they choose to do character level tokenization, which is silly in my opinion. Like, you can still do tokens. Why do you not use a tokenizer? This makes no sense. Like, it's so easy to just upgrade to a simple tokenizer and like a tiny stories or something data set. This is silly in my opinion. But first attempt, fine. I would love version 2 of the paper should definitely have tokenization and a bigger data set. Not huge. You can use tiny stories. That's fine. But like, Shakespeare is not quite going to cut it. It's unnecessarily complex for a network of this size, and too small of an actual data set, again, even for a network of this size. Now, evaluation metrics. This is more finicky, weird stuff they were doing. You don't need to explain training and validation loss to anybody. That's silly. Then the third one was inference speed, aka just tokens generated per second. The normal way to phrase that would be throughput, just training time throughput, tokens per second, right? So I don't know why we're even caring about this too much in the first place, given you obviously don't have an actual optimized implementation. So it's not even that this makes sense to measure throughput speed that much, but also you're calling it something weird, saying inference speed. Very odd. Here they list hyperparameters. This should have been a table, and they're missing quite a good number of them. It seems like they have no actual learning rate schedule, just a constant learning rate. That's pretty silly. And then they don't actually specify in terms of iterations. Like, you should clarify, like, is this one epoch of the data set? Or are you doing like, did you choose 5,000 arbitrarily and now you have 1.4 epochs or something? Because 5,000 iterations is a pretty big number for a batch size of 64 and block size of 256 on the tiny streaks per data set. I believe they're doing multiple epochs at that rate. I could be wrong though. Actually, I'm almost certain because we'll see in some graphs later they do actually overfit the validation loss. And just in general, reading through this stuff, it's very like ChatGPT written, like things are just duplicated unnecessarily. Stuff like here, this entire section was totally unnecessary. This is all just implied, had real like all been said, or just doesn't even need to be said given norms in the field. Very weird. And if they had phrased it as like we're helping beginners by spelling everything out, that'd be one thing. But they like didn't spell out lots of it, so it doesn't make any sense either. Like it's just obviously ChatGPT written. And to be fair, I want to clarify. I'm saying ChatGPT written. That's a thing you probably shouldn't do in general. I saw a study a while ago where people tend to assume ChatGPT written when what is actually the case is just English is just the person. English is their second language. Like in reality, people are very bad at telling if it's ChatGPT written, and they instead tend to mistake um, foreign people whose English is second language for ChatGPT because they just see like bad writing and assume it's ChatGPT. In reality, ChatGPT is like very good at writing. So I could be wrong here. There's this whole separate issue of like they could be just second English as a second language learner. The reason I say ChatGPT though is because there's so much duplicate stuff in here. Like it's just very repetitive in what they're saying, and it sounds like it doesn't seem like a person would write that much. Now, results section, they go out in paragraphs throughout here. They describe it, and they actually have a table also. They should have just stuck with the table and described the table. This was unnecessarily like just the formatting of this is terrible. But let's go one by one. The actual baseline they used had a fixed dropout rate of 0.2. Here's a problem, right? If your baseline is a 0.2 dropout rate, and then all of your decay, all of your experimental conditions have initial dropout rates of 0.2 and final rates of 0.0, that means all of your actual experimental conditions that they averaged a dropout rate of below 0.2. Now suddenly your baseline is just not applicable because your baseline has a much higher average dropout rate than all of your experimental conditions. What I would have liked to see instead was multiple baselines, one at 0.2, 0.15, 0.1, 0.05, 0.01, and 0. That's what I would like to see because of the fact that like these different dropout decay rates actually will end up having different average dropout rates because linear would be of 0.1, just a simple average, whereas exponential would be much lower than that because it's a lot of time at a very low dropout rate, right? I would have liked to see multiple fixed rates as your baseline, right? Then they get into loss, training time, and everything. Very weirdly, it seems that training time was significantly reduced from baseline to all of their actual experimental conditions. They had 500 minutes for their baseline, and then like 200, 300, yeah, like roughly 230 to 320 was the range minutes for all of their experimental conditions. Why was training time reduced here? That I don't quite get. So you are, instead of using a baseline dropout rate, you are using an actual decay dropout rate. So you go from 0.2 down to 0. My guesses as to why you'd have this speed up are, for one thing, just incompetence on their part and like just bad code and there's some issue in here. That's my most likely scenario because it shouldn't be this huge of difference. Cutting in half training time is wild. My first theory is just bad code on their part is why that this is happening right now. My minor-ish theories as to why you still could see reduced training time, I guess, despite the fact that, like, remember, they are iterating through every nn.dropout in the model during every training run, right? So you should be adding on another linear function, which like a linear time complexity function, right? But so the dropout, the applying of dropout itself, right, should be linear with respect to parameters. Maybe divide by a constant factor, so like 1/5 n or something, right? If you have a 0.2 dropout rate, just setting things equal to 0, assuming you're doing it very efficiently, just randomly. But then you're also having to iterate over every nn.dropout, which assume that there are 2 per layer, make that call number of layers. So now you have a separate term that is linear with respect to number of layers. Like you're adding runtime is what you should be doing. Instead, though, they have significantly decreased runtime. So assuming no huge bugs or anything, which they probably do have, assuming no huge bugs, my theories as to why you could have reduced runtime, again, I'm not fully aware of the complexities, is that maybe once you have a lower dropout rate, NN dot dropout is so efficient, you're actually doing far fewer operations with your low dropout rates. That's my big one. The other one just being the gradient graph being a bit simpler. You're now having fewer um, gradient calculations on all of those zeros. Um, but if it's the gradient graph being simpler, then you would assume that the point 0.2 dropout rate would actually be faster. So that makes no sense. And like it shouldn't actually matter gradient graph wise. Like you're just accumulating set gradients. Whereas it's probably if this actually is possible to get faster training time slightly with decay of dropout, it's probably just the fact that once you have a lower dropout rate, there's fewer operations per dropout application, right? That's what would be it. But again, this gap is way too big for that explanation. It's probably just a bug in their software, is my guess, but whatever. Also, they never clarified like what GPU setup they're using. It's definitely like Google Colab, like a single GPU or even a CPU, would be my guess. Although based off of 500 minutes, 5,000 iterations of Tiny Shakespeare, they've got to be using a Google Colab GPU. There's no way that, like this might be like an Apple Silicon GPU, but there's no way it's a CPU at that point. And then here, this is where they said annealing. They gave the results of their cosine annealing dropout decay, which they didn't even mention in the actual place they listed off and described each one. So another huge issue there, like just blatant mistakes, very silly mistakes, right? In terms of this table becomes very unreadable when you're making up your own acronyms for testing everything, like for your metrics. Why, right? Like we all know what training loss and validation loss are. No need to use final training loss. And then the best validation loss thing, this is, we'll see this later. This is a whole issue with them using best validation loss. This is very, very silly on their part. But you should have just done final training loss, final validation loss, and not said the word final. Total train time is fine, um, but average inference speed, it's just throughput, tokens per second. It was very silly, right? You could have just actually put the units in the table up here. Just not well done. And then the inconsistencies as well. Here they say that the validation loss-based adjustment schedule, while effective, resulted in increased training time. I think if I remember correctly, I'm pretty sure that it actually didn't. That they actually listed it off as still decreased time. I think they might have been saying relative to our other um, conditions, but like by default, when you say that, you mean relative to it should be relative to the baseline. But I think they were referring to relative to their other experimental conditions, what they were saying. But still, just like poor phrasing throughout, right? Here they have their actual training and validation loss curve. First off, they're flipped. You should have training on the left, validation on the right. That's weird, right? Second, look at these things, right? Look at these things. If you have results that look like this, first off, you should know that your graph is like obviously not at the right level of resolution, right? All these lines are actually together. So you can go ahead and cut off the first like somewhat iterations of your validation loss and training loss, and that way you get an actual easier to see differences. Second, they're pretty small differences still. And like when you look at this, look how we actually have an uptick in validation loss. So they overfitted these things. I understand the idea of like, oh, basic science, choose your conditions before you do experiments and then stick with them. But here, like, you should, even if you didn't know what overfitting was, you should be able to look into what overfitting is and go, oh no, we should have stopped at 2000 iterations. It's obvious this data set is too small to actually work here because the overfitting here is insane. Training loss keeps going down, whereas over like the validation loss goes up at this point. Like this data set is too small for 5,000 iterations at a 64 batch size, 256 context. Like it's too small for that, right? Next is like, why are there so few actual points? Look at how many times the actual lines kink. There's so few of these. It's not expensive. This is like a very cheap experiment. Like, do you have so few actual measurement points going on here, right? I should be able to, even at this level of granularity, I should be able to see ups and downs in the actual loss curve, like fluctuations as it goes down. This is pretty silly, right? And then, yeah, they chose best validation loss, not final validation loss, because they messed that up. So that was the reason why that happened earlier. Silly stuff. And then this is another issue I have with this isn't really their fault. This is the thing that happens in science in general is like authors will overhype their findings. I would love it if some authors would just say when they're done, our results are not good, don't use them. But instead, look at this. These findings highlight the potential of adaptive dropout as a valuable technique and for training large scale transformer models. Okay, first off, your results weren't really good, so no. And second, like you're not at the point where you can say that this generalizes to large scale models yet. Like you should have the self awareness to say like that. Like it's one thing when like a billion parameter model says it and you're kind of like, eh, maybe, probably, hopefully, but this like no. By dynamically adjusting the dropout rate, we can achieve faster convergence and better generalization. No, no, all right. Experiments are too small, and the odds that this generalizes better, like well, are dumb when like it literally generalized worse. When you look up here, like you can't even tell because all these lines are so close together, but like it didn't actually perform better. This is very silly. Um, I don't want to be too mean to people. Like, don't get me wrong. Like, this is obviously like a first paper and a reasonable attempt, and I would love to see a version two, version three, and they make it into an actual good paper. My guess is that they work at some company and they wanted to impress a boss who they knew wouldn't be able to read this paper and would assume like, oh, my workers are doing research. Oh, wow. That's my guess as to what happened here. I've seen it happen before. So don't get me wrong. I don't mean to be too mean, but yeah, this was pretty, on the one hand, pretty silly in terms of its lack of quality. On the other hand, like for all of you amateurs out here, not only should you try and keep the quality relatively higher than this, but also like remember you legitimately can post to archive stuff like this just to like as like a work product for your resume. You can do this. Like this is a reasonable thing to say like probably have to be better than this, but still like, you can post something like a tiny Shakespeare's data set and like do it and say like, hey, I had no resources, like at a job interview, I had no resources, but like I posted to archive and here's an actual I did all the code and everything kind of thing, right? Like you can do this. Um, so like hats off to them for doing it, right? Just for period for doing it. I'm being mean because they didn't do it especially well. But who knows? Maybe version three, four up on the preprint archives paper will be okay. But yeah, that's about it for this recording. End of video. Don't leave yet. If you got this far, you're gonna love this video or this playlist. Don't forget to like, subscribe, comment, hit the bell, all the YouTube things. Join the Discord server, follow on Twitter, connect on LinkedIn, and consider supporting me monthly either through Patreon or by hitting that YouTube join button down below. For as low as $1 per month, you can get early access to my videos. Or if you're a one-time payment kind of person, hit up my Venmo. And if you want to borrow my brain for a bit, consider booking a paid consultation video call. All of those links are over in my link tree. And yeah, end of video.